You got it. All right. So this meeting is being recorded. Um, I think I already went through that. Oh yeah, the chaser tickets. So if you parked in the parking deck, the one on our website, there are chaser tickets for that. So you don't actually have to pay when you go out. You have a very confused look on your face. The parking deck, yeah, the parking deck. Is it right here? That one? This one right here. So there's keep in mind there's a parking deck like right behind the building that is actually Booz Allen, but the one that's with the address, the street address for this one, is the one you're supposed to park in. I think you can't actually get into the Booz Allen one. I really don't know. I haven't tried it. All right. Oh, oh, even better. So these slides are now out of date. Oh, all right. There's the Wi-Fi. Hopefully, if you need the Wi-Fi, you're on it. Streaming. So we are streaming for anyone who wants to follow along on their laptops. If you do, I don't know why you would do this, but if you do, please turn the sound off so we don't get any feedback. Um, the other thing, meeting notes. So a lot of the things that we do here, what I'm going to go through on the agenda, we have notes, so you can actually go in and follow along. I even encourage people. It's a collaborative thing with HedgeDoc, so it's on Markdown, and you can add things in there, speaker notes, whatever you want to add in there. It's collaborative. Just be kind, be curious. That's the rule for that. So, um, here's our information. How many people know we have a website? Oh, good. How many people have been to the website? Oh, even better. All right. How many people know we have a mailing list, which has been around for eons? Uh, I did not know that. It's the Nova Lego user group. Okay. Hey, more the merrier. If they want to come in here with their Legos and so we have Mastodon Fediverse thing as well. There's a Discord server which, depending on the month, is busy. Sometimes it's not. Hasn't been recently. And then we have a LinkedIn group, which is not really all that active, but I mean, I do post the meeting notices and stuff there, so it's worthwhile joining if you do the LinkedIn kind of stuff. Um, all right, let's do an icebreaker. So we haven't done this in a while, and I wasn't very creative this month. So yeah, it's very difficult. So what I would like to do is just go around the room and just state your name, and then you have to say whether your tabs or spaces. You can be your name, be whatever you want, just whatever you want people to call you, or however you want to identify you. We're not interested in tracking you or anything like that. I don't have a privacy policy to put up, but the privacy policy is I don't care who you are. So uh, anyway, so I'm Andy Newton, as I already said, and I'm definitely a spaces person. So
Sravan Balaji, pass that around. I'm sorry. I'm more of a tabs person.
oh,
I'm Tom Gutnick. Tabs or spaces depends on the context.
Yeah, I'm Sri Thirupathi. Spaces. No, they're done there.
Dave Fuller, and I'm definitely tabs. As a matter of fact, I set up my tabs. I'm very particular about that.
Kirby Thornton, and it again is tabs or spaces depending upon context. Yeah.
Bjoy, and I prefer spaces if I'm in like a Vim editor.
Hey, Lewis, it's definitely tabs. Come on.
Mike Gallion, tabs.
keeping track. Seems like we have more tabs.
I'm Charlie Head and I'm retired, so I don't use either one.
Ron, tabs guy.
I'm Joel Hogan Dobler. I'm a tabs guy.
Lawrence, and I will go with tabs today.
Christine Krause and tabs for sure.
Bryce Krause and spaces.
John Place, definitely spaces.
Tim spaces.
Oh, there you go.
Sorry. So I think we have more tabs people than spaces, so I quit. I'm done. You guys can go. I would have too. I thought most people were in my career. I've always run into more people who are spaces than tabs. So anyway, all right. So jobs. So we still have the same two jobs from last time. The information are in the notes. One's for a database reliability engineer, and the other one's a security engineer. Anyone else know of a job that's available that might be of interest to this crowd? Going once, going on. I see Bridgeline people pointing at each other. Is there like what nature? Okay. All right. All right. So people who are Mac users, right? No, just kidding. All right. All right. So if you know of anything, you can put it in the notes, and that would help other people who are looking for jobs. So let's get into the news. All the links are in the notes if you want to see them. So, I can just look back there. All right. AWS has donated OpenSearch to the Linux Foundation. For anyone who was used to using Elasticsearch, they forked it some time back. I can't remember. Was it 2-3 years ago? So they forked it because Elasticsearch went to a source. What do they call it? Source available license or something like that. No. It was not a copyleft license.
Basically, the license that they use doesn't affect most people.
Yeah, so it is definitely something that you would not consider open source. Anyway, so they forked it, and they've given the actual everything over to the Linux Foundation. So, anyone play Grand Theft Auto? Yeah, I haven't played it in a long time, but apparently Rockstar Games has now banned all Linux users. Oh, there is. Okay, so if you run Steam, if you have Steam Deck or Steam OS. Okay. Cool. Well, it didn't affect anyone in this room because no one plays Grand Theft Auto anymore, right? Anyone play with Redis or Valky? No. What do you guys do for a living? No, just kidding. Yeah, I've used Redis before too. Valky is the fork of Redis, and it's a community. Well, it's a community fork started by AWS. Yeah. It really is a community fork, though, even though it was an AWS engineer who did it. But it didn't go into any AWS specific stuff. So Redis went to a source available license as well. And so the community forked it, and it's called Valky, and they just came out with 8.0. So that's So Redis is like it's an in-cache or in-memory database. I guess it's not SQL database. It's key value pair type stuff, and you have sets and lists and things like that, and so there's indexes on it, and it does have features to sync it to disk and stuff like that. So a lot of people use that as a front end caching for things that hit their relational database, so it's a little more performant. And it's got clustering and all that other stuff in there. You can use it for your main database if you know what you're doing. So, but anyway, so they just came out with 8.0, and apparently it's a pretty big deal. So it's more performant than Redis and has better observability and things like that. So they're pretty proud of it, which they should be. So, this is kind of interesting. So the Linux market share right now is $7.8 billion, or actually it wasn't 2 years ago, 2022. So there's this firm out there that's trying to figure out what it will be 10 years from 2 years ago, right, in 2032. And they've calculated it out to be $24 billion. So that's quite a big jump. So anyone who's into the Linux space, if you're an admin or anything like that, or if you're doing any Linux specific development, yeah, you'll probably see you'll probably have a good career for a while. So, anyone do 3D modeling or 3D stuff? Yeah, so there's a program that's been around for free called FreeCAD. They started it 20 years ago. They actually just went to release candidate 1. So, this is actually a pretty big deal for people who do CAD stuff because the only other alternatives were not really free. So so there's their Fusion 360 or whatever, and then the online one called Onshape, which is what I've used in the past. It's free to use, but everything you do is public unless you want to pay for an enterprise license. And all the other things are very expensive when you start buying them. Very expensive. Like they're not hobbyist type. There's no way a hobbyist is affording that. So, but FreeCAD has been around. They've been trying to get this out for a while. And I believe the backstory is there's some engineering company that got tired of dealing with Autodesk and started contributing a lot of code to the thing to get it to this state. So, so it's going to go to 1.0 release hopefully this year. So that's a pretty big deal. How many people are programmers? How many people have ever done Swift? Yeah, no, this is an open source language, by the way. So, so Swift 6 was just released, and it has it's pretty interesting. I've never done it. I've never used it, and my understanding is the Linux support is not that great, but it's an Apple thing. Supposedly, the big deal is it has a concurrency memory safety type feature very similar to Rust's borrow checker. I asked online about people who might know this, and they were just like, well, it kind of does, kind of doesn't. So it's kind of a concept that's hard to get your head around. But and they also have an embedded version now too. So you can see what they're trying to market. They actually are trying to compete against C and Rust. So specifically Rust. So I thought it was pretty interesting. It is open source under the Apache license. So all right. Yeah, so this is a new one. It's a new group that started called DC Systems. They do a lot of I just copied and pasted their stuff, but what they're about is discussing how computers work at the low level. So they get into very low level type stuff. That's the pitch anyway. So that is on the 8th of October. It's in the notes, by the way. You know. So that's in Vienna, Virginia. The open source initiative is holding an AI town hall. Again, this is on the 18th of October. This is an online event. So if you're interested in discussing artificial intelligence and the latest of what they're doing there, then feel free to participate. And then there's the Maker Fair, which is on the 20th. That's at the City of Alexandria High School. You have to get tickets, right? You do? Okay, yeah. So I was unsure about it. So $12 to get in. Yeah, they just want $13. You pay 12. See what happens.
So maybe it's like some dates where it's cheaper and expensive the closer you get.
Should be interesting though. So So that's good. So if you're into the things that the makerspace type stuff, then that's pretty cool. Yeah. So call for presenters. If you have a topic, so we're starting to run out of the people who have initially signed up back in March when we first restarted. So if you have something you want to present on, feel free to see me afterwards. Of course, I thought Darren was going to be here doing the emceeing, but that's why I said you could have him mispronounce her name. But he's sick today. So anyway, so if you have something, come see me, and I would love to put you on the schedule. We have nothing for October at the moment. In November, we have another artificial intelligence in the real world type thing. So we have a company called Cabinion, they're going to come in. They're a consulting shop, and they use artificial intelligence for their day-to-day coding and things like that. So they're going to hopefully give us some pointers on how you like. So our security, the one we had on security was really interesting about AI security, but they actually use it in practice every day, and so they're gonna let us, hopefully inform us how it works and what the limitations are and things like that. And in January we have another AI presentation. So for anyone who was here for the previous one, we had an AWS principal scientist sitting in here. He was basically one of the people that kept commenting. It was a good discussion, but he's going to come back and do a presentation on artificial intelligence too. So that's going to be pretty interesting. We have nothing set for December, so if you have something that you can do for October or December, I would love to hear it. So, and I'm going to hand it over to Sravan. I don't know why this text got cut off. So, but this is an introduction to the robot operating system in robotics. So, take it away. No, if it doesn't work. That's how we do it. Move fast, break things.
Robotics, you don't really want to break things.
Did it come up? Oh.
What to configure the displays. Oh wow. Okay.
You get to present from now on. So yeah. So anyway, if you want to hold this is you can either clip it on or whatever you or hold it. So when he takes questions, he's got some giveaways for people who ask questions. So these are Luxbox RISC-V. You call these things microboards or whatever, small SPCs, but they're basically for doing small projects and whatnot. But it is RISC-V, and it is small enough. It's catching me. It's got enough memory on here that you can actually get an entire Linux kernel on there. So it will run Linux. The downside is you have to use Windows to get Linux on there. I didn't know when I got them, but I mean these things are like $5 a piece. So anyway, so they'll have those for when you have questions.
All right. So hello everyone. Hopefully this presentation actually works. But so my name is Sravan Balaji. I'll be giving a presentation on robot operating systems, which I hope will provide you a light introduction to some fundamental concepts in autonomous robotics. I'll start with a quick overview of what robotics is, some examples of robots that you might have seen in the real world, how they work at an extremely high level, and how we use Linux to develop and deploy these systems, mainly through ROS, which is the robot operating system, which is kind of the main topic of the presentation. Included this picture from CNN of a robot interacting with some penguins. Tux is the Linux mascot, and there's a robot, so kind of fit the theme of today's presentation. So a couple of disclaimers. Oh, this didn't ship. Oh, there we go. So, while I'm not currently, nor have I ever been a government employee, I should still probably give a couple disclaimers here. I'm giving this presentation in my personal capacity. Any opinions expressed are not necessarily representative of the positions or policies of any of my current or former employers. Additionally, the information presented here is intended for educational purposes. So with that out of the way, someone decides to switch. Okay. So a little bit about myself. I've studied mechanical engineering, computer science, and robotics at the University of Michigan. Then I moved to Northern Virginia in 2022 after graduating. I first started using Linux, Ubuntu specifically, during college as part of my computer science education, but eventually migrated my personal computers to Linux as well around the start of the pandemic. If you're wondering what I'm currently using, it's Gentoo. Actually, I don't know if Chris does not. I feel like I met a guy named Chris. I could be misremembering the name back at the April NovaLug. I was using Arch at the time, and actually he mentioned that he's using Gentoo. I'm like, oh, that seems interesting. So I looked into it and started using it, and so far I like it. So anyways, I worked at a couple places like Rivian, MITRE, and now Metron on different kinds of robots. I'm currently working at Metron as a software engineer, developing software for unmanned underwater vehicles. I don't have any pictures of those, but I have some pictures from my time at other places. Like on the top left is a picture of the Rivian R1T. So if you're familiar, Rivian is the like electric vehicle company. I don't have any pictures during my actual internships there, but I ended up seeing a live truck later on, so took a picture of that. The picture on the top right is from my time at MITRE when I was doing some drone testing out in Arizona. So you can see me standing there. The bottom left was a class project I had during grad school where you basically had to have a robot arm pick up some blocks. Oh, this is annoying. Okay. So the videos aren't totally playing when I hover on the screen versus that screen, but I'll fix that as we go. And then the bottom right was also from my time at MITRE. This is the Mobile Autonomous Systems Experimentation Labs Jeep Grand Cherokee, sort of like an autonomous systems test bed. You can attach whatever sort of sensors you want to the computers that are running on board, and then you can see what are they seeing. Can you do path planning in the parking lot where it's relatively safe to drive around, that sort of thing. So I wanted to give a bit of an overview of what robotics is. Some of you may have come from a software background or networking or IT or whatever it might be. So maybe you don't know what robotics is, and that's perfectly fine. So I wanted to give some descriptions I found online. This one's from my alma mater. It describes robots as embodied intelligence that interacts with the physical and human environment. I think that's a pretty good description. There's also this one from Wikipedia. They call it a machine capable of carrying out a complex series of actions automatically. And then I'll kind of give you, what I like to think of in my own head. It's basically a combination of hardware, software, and some sort of intelligent decision making. I think this intelligent decision making is really the part that stands, keeps robots as a separate concept in my mind from, I don't know, like any other electromechanical system, like a toaster or a motor, something simplistic that doesn't necessarily have any decision making. So let's talk a bit about the types of robots that you might have seen. Drones are pretty popular these days. There's a quadcopter shown here. They're popular because the prices have come dramatically down since they were originally released. They have pretty decent battery life now, and they're fun to fly. And you can take pretty good aerial photography if that's what you're interested in. And that just isn't possible before because you couldn't really go up on a ladder or something and get the same type of perspective that you could with an aerial drone. It's a little difficult to get into this hobby in this area just because of all the restricted airspace around the Capitol, but if you're willing to drive out a bit further out or even find certain gaps in the airspace, you could theoretically do it. So another example you might be familiar with is autonomous vehicles. They use an array of different sensors and computational algorithms to map out their environment, avoid obstacles, and transport their passengers to their destination. I included this picture of Waymo here, which is a subsidiary of Alphabet, which is a parent company of Google. So they operate the self-driving ride shares currently in Phoenix, San Francisco, and Los Angeles, and I think they're expanding to some other cities. But it's probably in the news a bunch because you've probably heard Tesla's crashing into poles, and there are drivers being blamed or not blamed for things that went wrong. Another one you might have heard of, sort of industrial robots. These are widely used in the manufacturing industry because of the repetitive nature of kind of assembly line tasks. So it makes it a great use case for robotics where you just want a robot to do the same thing over and over again. But there are some sort of like collaborative type experiments that people are doing, like in this quipped GIF that I included. where you can have a person kind of wave a thing in front of the robot and it'll follow it around. So that's pretty cool. Another one that's a bit more sci-fi maybe, but it's quickly become reality is the humanoid robots doing parkour and things like that. So you might have seen this Boston Dynamics video. You know, one of the main selling points of this, this sort of form factor is that they can navigate environments that were designed for humans, as opposed to, I don't know, drones or wheeled robots, which are very limited. And, you know, they need, at least wheeled robots kind of mostly need flat ground, right? Whereas a humanoid robot could go upstairs much more easily. So that's kind of the main selling point for why people are developing these. Of course, I have to give a shout out to the company I currently work at. So there's a partnership between Metron and Cellular Robotics. So Cellular is the hardware provider. They make the unmanned underwater vehicles, and we, as Metron, developed the software for it. So actually, this domain, you know, I didn't really think a lot about it during my time in college, despite being from Michigan, which is known for its water. You know, I was in mechanical engineering, so we mostly dealt with like ground and aerial vehicles. So again, like I mentioned, it was kind of something I didn't really discover until my time when I moved here and started working at Metron. These are used a lot in industries like oil and gas because you can get you can easily inspect pipelines and other underwater infrastructure that's pretty difficult to do for humans. You can imagine that just operating a fully crewed ship to perform these inspections can be really dangerous and time consuming and expensive, of course. So there's a lot of interest from all these oil and gas and even defense companies to kind of automate that process or have autonomous systems go do that inspection rather than humans or remotely operated. And then I just want to give a little context here for one of the interesting things about underwater vehicles opposed to other sort of domains. It's very much you kind of just drop it in the water and then it goes and does its mission and then you hope that it surfaces so you can kind of go back and collect it and see what happened. It's very similar to the space domain, but it's very different from like ground or air where you probably have near constant connection to the vehicle itself and you have GPS access all the time pretty much. So you know exactly where it is and you know what it's seeing in real time. Whereas underwater is kind of, it's like a wind-up toy more or less, right? You just wind it up and you hope it doesn't fall off the table. And then if it stops, eventually you go pick it up and like, okay, what did you actually do? So I thought that was interesting to call out. Of course, you know, there's so many more. I'm not going to get into everything, but I'll call out a couple that I thought you may have encountered or heard of. So space, you know, satellite systems, or even, you know, the International Space Station, they have those robot arms that like grab onto things and pull little pieces of the station together or whatever. I haven't actually seen these, so I'm really speculating here. Consumer robots, you might have heard of the Roomba or other sort of like vacuums that are meant to go in people's houses and do sort of scanning of their environment and then finding the dirt and going and cleaning that up. If you've been to like Disney World animatronics, or even if you've heard of Five Nights at Freddy's, you know, the animatronics that, or like Chuck E. Cheese's, right? So basically these like robot characters that are meant to entertain children, I guess, but turn into nightmares sometimes. Exoskeletons, these are used a lot in for people who have like amputations or even in war fighting. You know, if you want to carry a large load, it's a lot easier if you have an exoskeleton holding that weight for you as opposed to having to do it yourself. Also medical, you know, if you've heard of these surgery robots that do the surgery on bananas or whatever from somebody sitting like 5 miles, or not 5 miles. Forget what, there's some metric. There was like a doctor sitting in the West Coast on their computer interacting with a robot that was operating on the East Coast or something ridiculous like that. I don't know if that's actually true, but that's a potential use case for robotics. So now I want to talk a bit about how robots actually work. Again, you know, assuming you're at this presentation because you want to learn about robotics, so you may or may not actually know how they work. So I wanted to talk through a couple details or sort of frameworks to think about to kind of try and understand if you read news articles and you're like, oh, how does that actually work? Hopefully this will provide some idea. So it's kind of helpful to think about robots in the context of how humans perform various tasks, right? We use our senses. Okay, there we go. We use our senses to sense the environment and gain information about where other people are, where we are, where, for example, my arm is in relation to my center of mass, so that I don't just go smacking things wildly. If you played Quap, you know, never mind. It's a game where you try and do like a marathon running thing, and it's very hard to move your limbs because it's a really weird control scheme. My point is, you know, robots have to know where their limbs are and where they are in some environment and where the obstacles in their environment are as well. So once you get that information, of course, you need to reason about it and think, okay, what do I do? So I know that I'm here, and I know that there is this TV in the way. So if I wanted to point here, I need to think about how do I actually maneuver my arm so that I'm able to point at the thing that I want to point at. And of course, once you decided that you actually wanted to move your arm to do that, you have to figure out, okay, how much do I pull on my muscle so that it pulls my arm up so that it ends up at the position that I wanted. So you can kind of think of it in like the sensing, reasoning, and acting sort of a paradigm as a mental model. So we can use that sense, plan, act paradigm to think about how Mars rover might work. So the Mars rover is a remote-controlled vehicle designed to explore the surface of Mars. Due to the communication latency from Earth to Mars, you can imagine newer iterations like Perseverance are increasingly trying to become autonomous, so that operators really just have to kind of give them a point in space, and then the robot figures out how to get there. If you want to kind of understand how this works, robots start by collecting data about their environment using stereo cameras and other sensors. And you can use the images captured from these cameras to build a map of the surface of Mars to identify obstacles or rough terrain. So you can kind of see some of these like red dots appear as obstacles, and you can see the surface of Mars when this video gets back to where it needed to go. And then, after figuring out a path, you actually need to control the motors to follow that path, right? So this video decides to play. The operator has given the robot a place that it wants it to go. You can see these little black lines are kind of its planning. Okay, these are the viable paths I could take, so let me choose one, and then how do I control my motors to actually follow that path that I decided? So now let's explore a bit of these categories in some more detail, starting with sensing. So one of the most popular sensors for various applications are cameras. These are specialized. There are specialized cameras like this one that can capture RGB images as well as depth. So you can use it to generate this kind of 3D point cloud, right, where you get this three-dimensional position of each of the pixels and the colors of the pixel, of course, with your typical RGB image. Although I think this is more of a heat map than an image. But the point being, you can get three-dimensional awareness of your environment rather than just a 2D picture. Another one you might have heard of if you've been listening to autonomous vehicle space is LiDAR. What LiDAR stands for is laser imaging, detection, and ranging. You can see kind of on the image on the left, it's a high-level idea of how it works. So it works by shooting a beam of light out and measuring how long it took for that light to reflect off the environment and bounce back to the sensor. So you can see that in this little toy box example, right, this light is bouncing off the environment used to generate these points of how far were those points. You might be wondering, okay, you measure the time that it took for that light to come back, so how do you actually get the distance? Well, we know the speed of light, right? So if you know the time and you know speed of light, you can figure out distance, then you can generate a 2D map. And then you can, of course, kind of extend this idea to more complicated scenarios like autonomous vehicles deal with, where you have this whole scene with a bunch of people walking across and trees and buildings and cars and things. And this, just due to the speed at which you can spin that LiDAR and get those measurements, you can get really good spatial awareness of your environment without having to do a whole bunch of processing like you do with cameras. So, there's a whole, Elon Musk is all like, oh, LiDAR is a crutch. I don't see why we shouldn't use crutches, but whatever, if you're concerned about the safety of people. But anyway, that might be it. Yeah, that's a fair, well, it's not really fair, is it? Because you're paying with people's lives. But again, this is my personal opinion. It's not reflective of any company. So let's move on to somewhat less controversial sensors, shall we? So the inertial measurement unit's another one that's pretty commonly used. So it contains a gyroscope, accelerometer, and magnetometer. The accelerometer, as the name kind of implies, measures acceleration. Gyroscope measures angular velocity. And magnetometer, which is sometimes included, sometimes not, measures magnetic field. So usually you combine this IMU into an inertial navigation system along with GPS to kind of figure out where am I in the world, what orientation am I at, what direction am I facing if you're concerned about sort of geolocation. There's really large and expensive ones that are used in spacecraft, like the one shown on the right, but these are actually much smaller. These are, you can put this connected to a Raspberry Pi and have it on a little mobile robot that drives around. So they're really not that big, but again, if you need really high accuracy and you're working in space. You know, you're probably able to afford a bit more fancy gadgets like this one. Again, well, I have limited time here, so I'm just gonna kind of gloss through that. There are many other sensors. You know, in the underwater space, we use sonar a lot. I mentioned GPS, which is a type of GNSS, but of course, other countries or conglomerate entities, whatever you want to call them. Like the EU has their Galileo system. I think China has Beidou. So there are many other satellite systems that can give you global positioning other than just GPS, which is what the US has. So that was the first category, right? So I'd like to talk about reasoning a bit. So hopefully this will continue playing. So imagine that you are kind of dropped into an unknown environment and you're blindfolded. So you have no idea where you are. You have no idea what your environment looks like, but you need to find your way out. So as a human, what you're probably going to do is, you know, start reaching your arms out, figure out where are the walls around me, where are some key landmarks, and maybe you feel that there's like something sticking out of the wall that is different from a flat surface. So you know that in this direction, there's a landmark that I can use to kind of figure out if I end up back here, I know exactly where I am because I've, you know, closed a loop, so to speak. So this idea is basically how simultaneous localization and mapping, or SLAM, works. So you can see on the left, you know, this robot has, for example, a LiDAR sensor. So I mentioned before, it measures the distance of obstacles around it. So as you move around and you measure the distance of your obstacles, you kind of build up this map. So, you know, as a human, if you were dropped in, you would do the same thing, right? You kind of figure out, if I started walking in this direction for this long, I know that this hallway is about this long. So if I walk back in that same distance, I end up at the point I started at. And you can kind of, again, this is a very large oversimplification, but this is how you would generate a map. And then let's say you do have a map, but you want to figure out where you are in the map. Well, there are techniques like the one shown here, which is a particle filter, which is a type of Kalman filter that kind of relies on just randomly spraying particles around your map and then measuring how likely is it that any given particle actually is where your current location is. So you just saw at the beginning, it spread all the, so it's like, here's my guess as to where I am, right? So at first it has no idea, so it spreads it everywhere. And then as you start moving around and as you start sensing, you know, if you, for example, if you thought you were here and you moved this far, but then you moved even farther and still didn't hit a wall, then you know that you're clearly on here, you're probably more likely in here because you had enough space to keep moving. So again, this is a very high level description of how this algorithm sort of works, but you know, a combination of these two gives you both a map of your environment if you didn't previously have one, as well as your position within that environment. Go ahead. No, so that's where simultaneous comes in, right? So it's kind of like you build a map for one time step, I guess, and then you figure out within your current, so it's like a local map, where you don't have a full global map, but you know that within the area that I'm able to sense at this time, I am at this, like, you kind of arbitrarily decide that you're at the center, right? So your world is centered on you. And then as you start moving, you keep the world static and then you start moving through the world. So it's kind of like an iterative process throughout time. So you don't go. Yeah, right. Because for localization, you kind of need to know where did you move, right? So if you know that you moved 5 meters, or if you didn't know, right, then there's no way for you to know where you are within your map. So you kind of need to have those types of sensors that give you location information. So, you know, gyroscope will give you orientation. Accelerometer is the one that gives you acceleration in your 3 axes. And then you can integrate that twice to get position. And again, if you're familiar with calculus, you know that when you integrate stuff, errors, or the extra constant term appears, right, which is basically an error term. So that grows over time. So that's where those landmarks come in handy, because if you know that, you know, you come back to a point that you previously saw, then you know exactly where you are, and you kind of eliminate that error that you were generating over time. Yep.
This algorithm really standard electronics at the time was doing it.
Yeah, pretty much. I mean, so it uses LiDAR, I assume. I don't think it has a camera. I hope not. No. Yeah.
Sorry, your robot vacuum, some have LiDAR, some have, I think they call it SLAM.
Oh, visual SLAM.
Okay.
Yeah, so the one I shown here is like LiDAR based SLAM, but of course you can do the same technique with the cameras, right? I showed before you can get the point cloud. So you can do this in 3D rather than 2D simplified example I included just for explanation purposes, but that's where the V-SLAM, which is visual slam.
So they'll use both, but they will
Yeah.
not both because we got that because V-Slam allows it to recognize things on the floor, and if it recognizes what the item is, it won't track over it. So if any of you have pets that like to sometimes not go where they're supposed to go, toddlers or cousins, and instead of having the robot smear something all over floors, it's a nice feature.
Yeah, so it's basically the distinction between 2D and 3D, and you can always combine your LiDAR, except you really only get like a plane of knowledge, right? Because it's kind of shooting beams of light around a circle in a 2D plane. So you kind of get information from that, but then you'd use your camera to get the 3D information and the object detection, which I think was, it'll be in a slide after this. So path planning is another one we should generally talk about. So let's say you do have a map that somebody's provided you, like, I don't know, the Earth, right? Or you're in some city. So you can think about how like Google Maps plans paths for you in, it knows all the roads that are available and knows that certain areas are not available because they're, buildings or grass or non-vehicle oriented paths, let's call it that. So there are many techniques to do this sort of path planning. I'm pretty sure that Google Maps uses A-star. Again, I'm not going to go into all the details here, but you can see one example here where if you generated a map for, I don't know, a drone, let's say. So it's trying to navigate around this mountain. So, while path A would be like the straight line path, which is the shortest path, it might not be safe because if your drone can't get high enough in time based on the slope of that mountain, you probably don't want to take that path. So then you would end up taking a path like path B, which is safer because you don't have to make elevation changes as rapidly. And then in the 2D case, there are algorithms. So I mentioned A-star, which is pretty standard. This one is RRT star. It's a rapidly exploring random tree. So I really wish these things would keep loading without me having to move my mouse. But you can see it's kind of randomly exploring the environment and determining what is the path that gets me from my start position to goal position. And then as it explores more and more, this path kind of gets refined. So that's where the star comes in, kind of the optimality guarantee. So it says, as you approach infinite iterations, you will get the optimal path. That would be nice. And then so I'm, you brought up the visual slam and the sort of pet identification or dirt or other object identification that Roombas will do. So the same idea is used in autonomous vehicles, right? You want to figure out where are all the cars in front of you. You want to know that these are parked versus this one is moving. So you can kind of more smartly plan how you're going to navigate your way through the city. Or for the Roomba, it needs to know, do I clean that thing or do I move around it? Or do I just run it over if it's like, dirt that I actually need to clean up? So that was reasoning. I mentioned sense, plan, act. So now we'll talk a bit about acting, which is actually, how do you move yourself to do all these plans that you've come up with? So again, I'm going to talk about the autonomous vehicle space because I kind of assumed that's the one that people might have mostly heard about. It seems like the Roomba might actually have been a better choice, but the same idea applies. So motion planning is kind of the idea of, if you're a human driver, you know that you want to either stay in your lane or switch lanes based on what the vehicles around you are doing. So you have in your mind, okay, if I turn this much, I will get into this lane. If I apply this much throttle, I'll speed up this much. If I apply this much brake, I'll slow down this much. Motion planning is kind of like, I can see all these dynamic obstacles around me. How do I, while still following this path, which was sort of that higher level path that like something like Google Maps would give you, how do I navigate around these streets and the lanes so that I don't intersect with my dynamic obstacles while taking into account the fact that this vehicle can't just teleport from here to here, right? It has certain constraints, like you can only turn the wheel so much. Based on that, it has a certain turn radius. It takes a certain amount of time for you to switch lanes or to slow down or speed up. There are limitations, so you have to take that into account when you're planning how do you actually navigate through the environment. Then there's a whole mathematical field called controls, which I wrote a couple notes in here, so I'll probably just read them out because I think if I tried to come up with this on the fly, it wouldn't go great. So as a human, we learn through experience how much you need to turn the steering wheel or how much you need to press down on the pedal or brakes to make your car do what you want. but robots need a way to figure this out too. And this is where, I mentioned this whole field of mathematics called controls comes into play. So it's all about regulating the behavior of a system using control loops. So there's sort of at a high level, there's open loop and there's closed loop. Open loop is basically you just map an input like a steering wheel angle or amount of throttle to an output like how much did my vehicle turn or how much speed did I end up achieving. Closed loop takes us a bit further by incorporating some feedback. So if you're going down a hill, your sort of intuitive understanding of if I applied this much gas, I would go this fast doesn't really work anymore because now there's gravity also pulling you down. So if you applied the same amount of throttle you would have on a flat street, you're going to go way faster than you want to. So this is where if you can actually measure, we talked about the IMU or GPS, which would give you, your actual speed, then you can figure out, okay, I'm going faster than I need to. So rather than keep applying the gas, I'm going to apply the brakes so that I slow down and actually achieve the speed I want to. Of course, the GIF wasn't playing, sorry. So this is really just scratching the surface. Again, I'm trying to give you high-level things that you can investigate in your own time if you'd like. Another one that I thought was interesting was reinforcement learning. If you've heard of the game Trackmania, it's basically like a racing game where you try to beat world records going around various tracks. This guy on YouTube used reinforcement learning, which is a sort of type of machine learning, or deep learning. This specific example is using DQL, which is called deep Q learning. Again, I'm not going to go into the details of that, but basically it gives you rewards for the farther you get along the track, the better score, I guess, the vehicle gets, and then if it falls off, it gets a bad score. So it's kind of incentivized throughout all this random exploration to figure out which paths will actually get it to go. This might be. I just included this little section because I thought it was interesting to show that, this technique doesn't really rely on the human to really design much other than the reward function. It's really like if you've heard of machine learning, the whole concept is you throw a tremendous amount of data and a tremendous amount of time in processing at a problem, and it kind of just figures it out. And it spits out a bunch of math that doesn't make a lot of sense to humans. But you hope that by tweaking some parameters here and there, you can nudge it in the direction that you want. So that kind of analogy really extends well to reinforcement learning because it's you tell them, I want you to stay on the track, I want you to get as far in the track as possible, and I don't want you to fall off the track. And then you can say, give certain weights to this one's more important than this one. And then it's just going to randomly try different things over many, many iterations, as you saw in the video. And hopefully it'll eventually figure out some combination of steering and throttle and braking that'll actually get it to do what you want. But again, there isn't really a direct mapping because again, it's relying on this deep learning. If you're hoping that the changes you make to the reward function result in the results that you want. But it's not the same as like, controls where you kind of have an intuitive understanding that if you raise this gain, you're going to more aggressively turn or something like that. Again, there are lots of politics and why you might use one or the other type of technique. But sort of the main benefit is for problems where humans don't have good solutions yet. That's where we just throw machine learning at the problem and hope that it works. And if you throw enough time and money and data at it, sometimes it does. Oftentimes it doesn't, but again, I'll stop that discussion there. So now let's move on to ROS, which is the robot operating system. So it's kind of the main thrusting force behind my want to make this presentation in the first place. You might be wondering, this is a Linux users group. I haven't really talked about Linux at all up to this point. Well, this is where it comes in. So you can think of ROS from the website. I got this picture. It's basically a combination of plumbing, some tools, capabilities, and a community of people who contribute to those tools and capabilities. But sort of the main thing that ROS itself provides is that plumbing. I'll talk a bit about why that's important. So first, some history. Where did this project come from? So ROS originated out of some PhD students in Stanford, Eric Berger and Keenan Weierbeck. They went on to join a Silicon Valley startup called Willow Garage in 2007, and that's when they initially made ROS open to the public. In 2012, Willow Garage created the Open Source Robotics Foundation, which took over as the primary maintainers for ROS in 2013, and then they renamed themselves for some reason in 2017, but they continue to be the current maintainers. So I don't know if I mentioned this, but ROS is free and open source, so it's worth talking about the details there about what that actually means. So I pulled this straight from the website. So ROS is primarily licensed under Apache 2.0, so it makes it free for both commercial and research use. The majority of community packages are typically licensed under various open source licenses, but if you have a particular package you want to use, it's probably best to check that package's license because it may or may not adopt the suggestion that ROS makes for their core packages. Okay. So you might have heard of the concept of distributions in Linux. So there's a very similar concept in ROS. And the reason that this is the way that it is because ROS is built on Ubuntu's distribution point releases. So there's also this concept of ROS 1 and ROS 2, which I'll talk a bit about. So ROS 1 Noetic is based on Ubuntu 2004 Focal, and then so that's the one on the left. ROS 2 Jazzy is based on Ubuntu 2404 Noble. And then you might be wondering, why is there a ROS 1 and a ROS 2? Well, as I mentioned in the history, ROS started in 2007. So a lot of things have changed since then. They kind of learned a lot of lessons about architecture and better ways to do things. So they kind of hit a point where they couldn't maintain backwards compatibility the same way that they wanted to. So that's why they ended up splitting it off into ROS 2. Although if you have ROS 1 packages, there are ways to make them communicate with ROS 2. It's just a little hacky. It's not kind of built into the core functionality the same way that if you had built a package for ROS 2, it would work semi-natively compared to a ROS 1 package. So ROS and its associated tools are best supported on their respective Ubuntu point releases. I think there's also support for Windows 10 for ROS 2. I don't know how that works, but there's also experimental community support for other Linux distributions like Red Hat Enterprise Linux or Fedora, Mac OS, Debian. I'm sure Arch probably has some community of maintainers out there. But if you want the best experience, it's probably best to just stick with Ubuntu or run ROS in a Docker container, so you can run it on any Linux distribution and not worry about all the installation headaches that might come up. So let's talk a bit about ROS concepts, right? So I mentioned that ROS is despite the name, it's kind of more of a software framework than an operating system. It's sometimes called a middleware. Basically, it's the thing that goes between your various programs. I at the start of this presentation, I walked you through a whole bunch of concepts, right? So you can imagine robotics is a very difficult field that requires expertise in a whole bunch of different things, right? It's not just software; it's also electrical hardware, mechanical hardware, firmware. It's a very wide-ranging set of skill sets that are needed. So the way that robotic systems are typically built kind of follows the Unix philosophy, right? You try to build one thing that does that one thing well, and then provides outputs for other systems, which will take those inputs and then do something with it and pass that along to some other program. So for example, you might have a hardware driver that processes the raw data stream from a camera to some standard image format. Then you pass that along to a computer vision program, which detects, here are my obstacles, and then passes those along to a motion planning program, which is then going to figure out, how do I navigate around those obstacles that you just identified? And then that's going to have to pass it along to some motor controller that says, okay, now I know what I want you to do. What electrical signals do I send so that I actually rotate my wheels at the correct speeds relative to each other, so I do my turning and speed up maneuvers in the way that I want. So again, how do all these programs work together? Well, this is really where ROS and really any other middleware solution comes into play. So in terms of like a mental framework, think of it as a graph where the vertices, or nodes as they're called in ROS lingo, kind of represent each program. And then to connect these nodes together over an edge, you need some sort of interface, right? So if people work in IT or networking, you probably know a lot more than I do about communications. So you might be familiar with like TCP/IP or UDP or multicast. These are really just buzzwords I'm pulling out. I really don't know what they mean. But the point is, you need a way for your various programs to communicate with each other, right? So ROS provides these three different types of interfaces. Messages kind of follows the publish-subscribe model, where programs that need certain information subscribe to a topic of interest, and then programs that provide that information publish to that topic. So it's actually very similar to what I'm doing here in this presentation, right? You are all subscribed to the ROS topic, and I am publishing on that topic, and you are all subscribed to that ROS topic. The next one is services. So this kind of follows a request response model. Again, if you do like web dev, this is probably more familiar to you. I don't, so I have no idea. You make a request to a website and then it provides you back some information, and then you do something with that. So that's probably very natural for those of you who work in that space. Actions are very similar to services, except they're typically longer running and they can provide feedback of how the thing is going during that time. So maybe a very poor analogy that I came up with was like you leave your car at the auto shop and then they call you back every few hours and like, oh, okay, we fixed this, we fixed this. Oh, this thing's broken. So do you want us to do that, or do you want to fix that yourself? So you kind of get updates over time, but it's still very much like a, your request that they give you updates, they respond with those updates, and you can also interrupt them and say, what, I don't want you to fix that. I'm going to go somewhere else, or I'll deal with it. So you have those options with actions. And again, like I mentioned, for those of you who actually know how communications and networking work more than I do, you might be wondering, how does this actually work in ROS? Well, it uses the data distribution system, or DDS. And again, I just pulled these straight from their website of why they claim that it is good. Low latency data connectivity, reliability, scalable architecture, and security. I'm sure you could drill down to each of those points and push back, but again, I don't know enough about this particular part of robotics to really comment. So DDS is an open standard, but of course you have to have people implement those standards. So there are a couple here that the ROS2 documentation lists as sort of supported vendors. Some of them have what they call tier 1 support, which is they're very integrated well into ROS, and then there's like tier 2 and tier 3, which are you may end up having problems. So community might help you or figure it out yourself. It's kind of the intention there. So now that you're able to pass these messages back and forth between your processes, you can imagine if you are deploying a vehicle out in the field to do some sort of test, right? You want to be able to record all those messages that are passed back and forth so you can replay them later and kind of have like an asynchronous digital twin, if you want to think about it that way, to see, what did my vehicle actually see? Why did it make that sudden left turn? Because then you can play it back in your sort of simulator or visualization service and see exactly what it saw. And then you can see, oh, identified this object, and it was actually a tree, but it thought it was a cat, so it made a turn. Right, so it helps you with debugging. So there's this tool called ROSBag, which lets you record and replay those messages. So I thought I'd just point that out as a sort of useful feature that ROS provides. So if you're a software developer or you work in robotics, you might be wondering, how do I actually write these programs that communicate, and what does ROS support? Well, officially it supports C++ and Python, but there's community support for all the other ones here, like C or Java or C#. But I don't really know why. Oh, maybe Windows app. Okay. JavaScript, Rust. But these are all, again, very community supported, not officially supported. So that's pretty much the end of what I wanted to talk about, but I included some demos here. We're at about 38 minutes, so I figured I'll probably just play one of these to give you a rough idea of what you can do with ROS. So here, I think this is just. Oh, go ahead. I don't know what PMC is.
There we go.
Well, again, I don't know what that is, but
Basically, it's a phone that is hardware set with proprietary.
And what does it do?
You program to tell the robot.
Oh.
So like, you tell it go left, pick up, go right. Just do it over.
Oh, so yeah, you could easily replace that with a C++ or Python program that publishes ROS messages that, I guess however the PLC works to communicate directly with the robot, it would need to listen for those ROS messages and then translate them into whatever that like control API is. So ROS, again, I mentioned like the main benefit of ROS, I guess, is this plumbing, is the idea of how do different programs communicate with each other. So you might have a very low level, like the PLC, that communicates directly with the robot, but maybe you want to have some other process that gives a higher level command to the PLC, which then translates that into like the voltage or whatever that it sends. Yeah, so, well, I guess it depends on the type of computer you're using. If you're using like a Raspberry Pi with, ARM CPU architecture, you might have to compile a bunch of packages from source if they're not already built binary for ARM. If you have like a traditional x86 computer, like you might have on a autonomous vehicle, right? They're a lot bigger, so they can have like desktop grade computers in there. So they're going to have typically x86 architecture CPUs. So you might have binary packages for everything. So in that case, it's slightly easier to install because you don't have to run into, oh, I didn't have this dependency, or oh, I didn't have this compiler set up with whatever flag I needed, or things like that. But it's not that hard if you follow the documentation instructions. Or actually, like I mentioned, you could kind of skip all that and just run it in Docker containers. So really, if your robot has some flavor of Linux or really anything that has Docker installed, and then you develop all your various services in Docker containers and you just deploy them to your robot, it will basically work using ROS. So you don't have to run natively. Actually, one example I heard before is that what I think at MITRE, so one company had a robot that was just going to run Docker, and then a whole bunch of other companies were going to contribute different pieces of this puzzle as Docker containers, just to kind of simplify the whole it works on my machine, the whole dependency hell kind of problem. So no, you don't have to install it natively, but even if you did, it's not that difficult. I would suggest that you do it because things like GUIs are kind of tricky and annoying in Docker. So if you want to have like all these visualizations I just showed you, it's really hard to do that in Docker sometimes, depending on your host machine settings. So you might be better off just running a virtual machine and running Ubuntu with ROS installed, so you can listen to all the messages that your robot is sending, and then have like that digital twin I mentioned, so you can see my real life ARM. Actually, I kind of hope that one of these videos would have that. Might be this one. I think they have a camera as well as. Oh yeah, so you can see in the real world, this is what the thing is doing. And then here are some visualizations of the point cloud that it sees, the map that it's building, and then here's like the simulated environment that it's running through. But you could extend that to the real world, of course. So it's pretty good. Yeah, I mean, at least for getting started. In terms of like how do you set up a node to pass messages to other nodes, it's not that hard. I mean, the real hard stuff is like actually what do each of these programs do, right? I went through the whole start of this presentation with all these concepts like machine learning, computer vision, SLAM, all these things are really the hard parts. And actually, honestly, a lot of the main reason you might want to use ROS is you can just get packages that do those things that other people have written and contributed to the ROS community repos. So it's really the community and wide range of support for hardware that is the main reason to use ROS over other types of middleware.
So, figuring out applications, obviously,
Yep.
Is there a concept of like dependency watchdogs, HA type ideas,
No, I don't think it's built, as far as I know, I don't think those types of things are built in. It's kind of up to the user if like you want to have some monitoring process that checks if this one stops publishing heartbeats, then something's wrong, I should probably stop. So no, I don't think it's a built-in thing, but you could pretty easily write some error handling into each of the services that if I stop hearing from the thing that needs to tell me what to do, I should probably notify my like high-level decision maker, hey, something's gone wrong, I can't resolve it, you should probably stop. Do you have a question? Go ahead. So I think it really depends on your application, but they don't have recommendations per se. I mean, they can say that, for example, ClearPath Robotics is a company that does a lot of work to bring ROS support to lots of different hardware. So like the Spot robot, that's a Boston Dynamics robot that doesn't natively have ROS support, but they built some tools that available in the community packages that let you run, Boston Dynamics hardware with ROS. So, again, it's like how much work do you want to put into it, right? Do you want to write all that low-level hardware driver stuff yourself, Or do you want to choose hardware that is known to already have a ROS package? So it's a bit simpler from the user perspective. But the same with Linux, right? Like you could choose distributions that kind of work out of the box, or you choose ones that you have to build yourself, like Arch or Gentoo.
I was just gonna say the submarine thing, pretty cool. I actually worked for a company, several years ago where, one of the things they did was they dropped buoys in the ocean. And, at one point, one of them came back up and I had to, shell into it to, change a couple of things. They told me, like, if you put it in the data wrong, it'll go down and never come up, and you can't send signals to it into the water. For that deep.
Yeah, so that's like, I mentioned at the start, I currently work in underwater robotics, and sort of the main pain point is you don't have constant communication, and you don't have location information other than INS, because GPS can't penetrate through the water. So you don't have like a global navigation source until you surface again. So, and like, unfortunately, as has happened on a couple of runs, we let the vehicle go out, do its thing, and then, after an hour or so, we're like, it should have been done by now. And we haven't heard any pings. It's kind of concerning. And then we figured out, okay, yeah, it's probably sunk and it's stuck at the bottom. So we had to go recover it. So yeah, like, different domains of robotics have their own challenges. I think space is also pretty cool, but of course it's super hard to physically get there and to communicate once it is there. But like ground and air are a lot easier. But also air, it's like if your motor stopped working, you crash. With the ground, if your motor stopped working, you just stop. So it's a little safer in that sense, unless you're like in a busy street and now everyone hates you. So go ahead. So it's not industry standard per se, but a lot of companies do use it just because it has so much community support. Like even the company I work at, Metron, does not use it, but we use DDS. So it's really just, I mentioned the main feature is like that communication, right? So you could always roll your own version of ROS. It just, you lose access to all those packages the community might have built, because we build that ourselves, right? We don't necessarily just take off the shelf autonomy, because you don't know what's in there and how well it's going to work for your application. So we kind of have to build it from scratch, more or less. But that communication standard can be whatever you want. So we chose to use DDS probably for the same reasons that ROS did. But again, there are many other middleware solutions. I think I have a slide on that. So I listed a couple from Wikipedia. I haven't actually used any of these, but you're free to explore them if you choose to. But the reason I bring up ROS is it is the most widely used, and especially in academia, even in industry. A lot of industry uses it, but for sensitive industries like defense, they might not, because they have to be really careful about the source of that autonomy software. So they kind of end up rolling their stuff themselves rather than pulling off the shelf. So I've listed a couple learning resources here. I think somebody asked a question about how well the documentation is to help you get started. So there's a getting started page. There's even a discourse site and a general robotics stack exchange if you have questions about all those things I talked about at the start of the presentation, outside of the implementation details of how do I get this thing to talk to this thing, or how do I get this hardware supported. If you have questions about like, how do I implement SLAM, or I was going to try and pull out more examples there, but that's a good place to ask it. Also, again, I mentioned ROS discourse if you have ROS specific questions. Docker Hub, so I'd very much recommend if you're just trying to get started and you don't want to go through the hassle of installing all the packages on whatever distro you're using that may or may not be Ubuntu, just use the Docker image. You're going to have a bit of trouble with GUIs, but if you're willing to investigate the what's like xhost plus, and then you pass in some display environment variable, there are ways around it, right? Or just roll a virtual machine if you're that concerned about it. But there are many free resources online. There are even like paid courses on like Udemy or those other like online class things. So I listed these here. You're free to look at these after the presentation, but that's pretty much all I had planned for today. Forgot I was supposed to hand these out.
So
How about we just do a random sample?
I think you just chuck them into the audience.
Well, I will pick out a couple of people who I felt were brave enough to ask me that. So you seemed hesitant at first, so
Very good, thanks.
I'll also give you one. Thanks. The guy with the beard. Actually, you work here though, so. They are volunteers.
All right. I'll stand in the way of that. All right. So we're gonna stop the recording in a minute, and what time is it now? So 11:22. So we have this till noon, so you guys can stay around, talk to each other. I asked for a presentation for next month, and I already have one. So there we go. John's gonna do one on Let's Encrypt and Ansible. So good, because my experience with CertBot has been pretty poor, but and you're going to cover Acme, the Acme protocol and stuff as well. Yeah, so it'll be pretty interesting for anyone who's ever done Let's Encrypt type stuff. It's going to be a useful presentation. So if you have something you want to present in December, I would love to hear from you. And I think that is it. Anything else we need to discuss? All right, thanks everyone. And remember to validate your tickets before you leave.